Hey everyone, and welcome back to the Information Bottleneck. Um, I'm Ravid, uh,
And I'm Alan.
and we'll talk today about so many things. So I'm glad that you join us. So we'll start with some news like that we heard about in the recent week. I think the most exciting thing is about the new Google model, Gemma, 200 Gemma 3, 270 million parameters, um, and it's quite crazy that you have such a small model, that basically you can use it for everything almost. It has 170 million embedding parameters, right? And 100 transforms block, 100 million parameters that are the transforms. Um, and like even the BERT from 2018 was larger. And I think it's something that we will see more and more, right? That like a small model that you can use and you can tune and you can use your own data. Um, and you don't need all these general purpose huge models in order to solve very specific problem. So I'm glad that Google are going in this direction. I think this is it's very important for so many use cases.
Yeah, and edge devices are a really growing market for these models. I mean, we've talked before, I think even on our first episode, about the importance for a lot of use cases and for users of private models. And a model of this size, you can run this easily on hardware, probably from even before 2018. And that probably means that like 2022 plus cell phones hardware should be quite capable to run a model that, when you're squinting and when you're not looking at like reasoning performance and just want some like, give me a food recipe or something, is probably pretty close to ChatGPT, and that's extremely remarkable. I'll also point out that there's even been, just you mentioned BERT, there's been at least one follow-up paper being like BERT revisited, where they kind of tried to like go back to the original architecture, like the bidirectionality, and even I think the encoder decoder approach, and see if there's anything still there, right? And they've at least updated the data set that it was all ran on, and I think there's been an equivalent update even for older stuff like Glove and Word2Vec. So we do need to keep our older methods alive, especially because some of them might really have just been as good as the architectures we have today, and didn't have the compute or data sets applied to them that we now have.
Yeah, I feel that like this is something, yeah, even more general, right? Like you remember that, for example, in the past there was a huge debate like what is better, convolutional networks or VATs. At the beginning, like convolutional networks were better, and then VAT was much better, and then there was a paper, I think it called like revising ResNet or something like that, right? That basically show that, yeah, let's take all the tricks that we know from VAT models and let's apply them to convolutional networks and ResNets, and you will get very similar results. And I think this is something that we see many times, right? It's like there all like tricks and things that we thought are so important for our training and for our performance. It looks that at the end it doesn't really matter, right? um there was a paper a few months ago, for example, that remove normalization layers, right? And apparently you can use, again, it may be a bit harder to stabilize the training, and you need to use another trick, but it's not something fundamental to your performance and fundamental to get very good performance. So the question is like, what is the magic and what is the why we get such results? I think it's an open question, and for me at least, I don't know. I think there is something like that in this combination of hierarchical networks with SED or something like that. But what exactly make it? I'm not sure that there is someone that actually knows the answer.
Yeah. Yeah, I fully agree. I fully agree. Just sort of, and even I think we'll talk in a little bit and allude to terms like the bitter lesson and things like this make the original bitter lesson essay feel real sometimes.
Yeah. So if you mentioned the bitter lesson, so maybe let's talk about it a bit, right? So I actually read a really nice blog post of Ben Recht, I think, that he, he described the bitter lesson as one of those researcher magic mirrors, right? That you can see whatever you want to see, and I think this is I totally agree with that, right? Like, okay, so what is the bitter lesson, or like what is the what most of the people think is the bitter lesson. So this is a lesson, okay, that posted by Richard Sutton in 2019, that basically says that I rephrase it, but it says that like it doesn't really matter the specific algorithm that we will use, but scale, like you scale the parameters, or like you scale your compute, basically give you much better results than to choose one algorithm versus the other one. And I think in general we see it in the recent years, right? In the area of deep learning, we see let's scale everything, and the exact details don't matter, and you can change the learning algorithm, or you can change the activation functions and things like that, but you will get the most the most effective results you will get if you will scale your compute.
Yeah, So I read this blog post. First of all, the name of the website is Argmin, and that's the name of my favorite workshop in all of machine learning, the argument mining workshop. So I just have to give a shout out for namespace collision here. Second, I'm very sympathetic to the original bitter lesson post, and I actually do not care for this blog post and think that this blog post was a shallow dismissal for the most part. In particular, his accusation that Rich Sutton is mostly looking at, quote, parlor games in reference to chess and because chess is a primary argument here. Now, part of why I think that this essay is so compelling is when I was super into AI, like as a little kid. Basically, I'm for those who don't know, I'm like 29 at this time, clear back in, let's say, 2003, 2007, 2000, various years of my life, I knew that I was really into games like chess and any type of strategy game, but I also knew that it's really hard to like grind and like be good at chess. Like it's really, and I'm still bad to this day. I'm really like 1200 elo or worse, kind of.
For people that don't know, Alan is like a professional debater player.
yeah. I claim I'm good at this, but I'm not good at chess. The reason I bring all this up is I knew this, but I was like, okay, well, I'm going to race chess computers. And being like 12, you can imagine that this did not make me popular with most kids, right? But so I grew up learning about this world because so at the time I was doing this, Deep Blue had come out, but chess engines, as in the type that could run on your desktop and beat grandmasters, was pretty new. And this was actually really exciting. So there was a bunch of companies racing with each other in a race that if you like look at the timing of all of this, it looks just like the current LLM race today. There was big players like Rybka, Fritz, Chessbase, and then Rybka got in trouble for stealing code from open source and not attributing it, got like thrown out in 2009. It was like big drama at the time, right? Where they were like the top engine for 5 years. It's like learning that, Lance Armstrong's doping, that kind of level of scandal. So the point being, though, that there's all these lessons that Rich is alluding to, right? If you look at all these chess engines and look at their code in C++, they are full of heuristics. Basically, most of the time, chess masters that were also pretty decent programmers sat down and like analyzed like every possible rule you can imagine when you combine it with Monte Carlo tree search, alpha beta pruning, open books to endgame table based. Like they threw this hodgepodge. And then, you know, years later, Google people just say more compute, self-play a bunch of video games, like a bunch of games with each other, and then that ends up beating what was like the best at the time of this old school technique, or heuristic based, like hodgepodge of heuristic based techniques, Stockfish. And now, of course, it's a little different because Stockfish and all the chess engines that are at top today kind of use neural network like influenced, they've integrated each other and turned into the synthesis of both techniques. But it's definitely leaning more so every day or year on relying on the neural net evaluation. And I really think that this is influential because I think that if you look at other board games, too, or like Diplomacy, for example, which is especially amicable to LLMs, Stratego, which I think is the next frontier of AI research and is my favorite board game of all time, you're going to see these same lessons. So I think that, using the bitter lesson as a shallow dismissal itself of techniques that are effectively supposed to use human ingenuity to help AI systems along on the path of recursive self-improvement is bad. But as a guiding star that more compute is good and more compute is responsible for a large amount of the gains that we've had recently, I just think it's true. And I'm sorry, like his examples are great. I spent a lot of time in the chess world, and his experience tracks 1-to-1 with mine. So, anyway.
Yeah, I agree. I just think that we need to be careful because, in retrospective, right, that now after you have this new method, and now you can try to align some old tricks with this new method, that's fine. You will probably can get the same results, but in real time, it's really hard, right? It's really hard to know what is the right trick that can help you to scale up the thing. So it's quite of a balance. I agree that scaling up things and scaling up compute most of the time will help you, but it's not that now, okay, everything that you will throw on it can make a better result. So I think we still need to be careful here.
Yeah. You're absolutely right on that. I will I'm going to go back to the chess example because it's so good again. So if I were trying to program a chess engine from scratch, by the way, a great thing to try to do, I know it sounds hard, but computers are so advanced that the moment that you put any extremely basic logic of how you should, decide how to play, hey, maybe I should look at the board, and if a move reduces my material on the board, that's negative. I want to downweight my scoring function. When you put the most basic stuff like that in, your modern computers put you already up to 2300, near Grandmaster, right? And then when you start plugging in the opening book, which is basically the equivalent of a pre-trained embeddings model, but the chess version of that they had 20 years ago, where it plays the first 30 moves ahead of time for you, and then the endgame table base where it perfectly solves the game once you're at 7 or 6 or whatever pieces they're at now, or fewer on the board. These push you over the edge. So it's almost, trivial in the sense that second year motivated computer science student would be able to write a chess engine that is better than certainly average grandmaster. And I would claim that fourth year highly motivated student can definitely write one that is better than Magnus Carlsen, right? So and that wasn't 5-10 years ago, right? Obviously it was harder to program in C or C++. They didn't have as much good starter code like PyChess, for example. I've written chess engines in Python, but the point being that back then, had you put all the equivalent amount of logic in, the chess engine would have been way better than me, probably 1800 master, IM, these kind of levels. So at least in games where we have perfect information, right? And a reward function where like it's a game tree, but we're reasonably sure there's either like a guarantee of draw with perfect play or almost certainly white wins, right? It's like one of those. I think that means like zero sum things probably do fully get accounted for in the bitter lesson, right? And I think that a lot of life looks kind of like chess. it's
Yeah, I agree. I think you also like chess is a good example of we need to look on the representation. Like we need to look how we represent the data, right? And how we feed the data and how we clean, or like what is the important parts that we actually care about in our data. Maybe we'll do an episode at some point.
Yeah, there's stuff about how you represent games, bit sets or whatever, like more efficient. I went deep on this, Ravid, on my like independent of working with you. So I'm anyway. Yeah, let's do it.
I agree. We'll do it. Okay, the next thing, I'm not sure if you saw it, but this week there was the 2025 World Human Robot Games, the Olympic Games for robot, and you can see a lot of clips and a lot of short movies of robots that running and jumping and trying to do sport activities that are supposed to mimic humans, but they are really bad and really funny. Like it's crazy the difference, between ChatGPT that answers as human and like you can think is human most of the time, and these robots that they fall down, they fall apart, like they go to the wrong directions, they don't know how to jump, and I think it's very interesting to ask why is that. I just read another great blog post of Sergey Levin from Berkeley that the title is LLMs are like prisons in Plato's cave. That basically says that what is the difference between text and vision? Why LLMs are so good when we train them on text, right, versus vision models that are fine. And of course I'm not even talking about robots, like even just pure vision models. So what is this, why we see such a difference? And he claimed that LLMs are trained on text, and text is some kind of like humans or like filter to the human thoughts and like to the human perspective and how we look about the world. And if we are training LLMs with these kind of data, we give them something about our brain and about perceptions. It's some vague, very vague and blurry data about us, but still it's filtered based on humans, versus videos or like or vision that we have the exact physical world, and we are not passing it through humans and through our thoughts and what we think about the world. It's much harder from one hand, right? It's much harder to learn directly from the raw data, but from other hand, it may be help us to go behind like the current limitations of LLMs and like to understand the world, to understand the physics of the world and what we can actually do better compared to humans.
Yeah. I'm really glad you brought and connected both of these stories together. The first one I'll point out is the blurry mirror analogy is really excellent for what we're doing in machine learning in general. We have to take input data in the case of text and formulate some way to account for every possible bit of English or that you could ever possibly write, and we call this tokenization. In the context of the design of neural networks for processing image or video, if you tried to process every single pixel out all the way through in its full what do you call it, dimensionality, like neural nets that kind of match in some cases like 4K, like the amount of pixels, today's computers probably like building in some cases on super big video, like whole covering like a country in data centers wouldn't be enough compute for so what people are forced to do is ultimately what is called dimensionality reduction. It's sometimes thought of as a subfield, but it's at the heart of what all pretty much all models are doing, and they're reducing the representation, and we actually call the reduced representation things like latent or hidden space, which is our admitting that we have no freaking idea. I mean, we have some idea, but very little idea of what's going on in these a lot of times. And thus it becomes computationally feasible. So really the argument is that the blurry mirror is the only thing that the computer can work with right now, and that it's our job to make it a little less blurry, and whole papers get orals and everything for successfully proving that it's slightly sharper. I was also just going to point out the source and connect to two other things that have been talked about a bit in prior, I would say, historical like AI discussions. So the first one connected to why we see all like relatively maybe not as great physical control systems with robots is a thing called Moravec's paradox, right? And Moravec, what Peter Moravec, or I forget his name, but he is like trying to understand why even back in the late 90s it was so easy to create superhuman chess software, but impossible, so to speak, to create like physical control systems that were reliable with any kind of the real world's problems. And he concluded that the things that humans have evolved over millions of years to do constantly, such as like movement in the world and all these are the things that it's going to take in a equivalent like millions or billions of computational years, which I mean we simulate with fast computation, right? But like it's going to take a lot longer than contrived activities that humans weren't doing for very long, but can quickly become really good at. So like chess, like, chess has actually existed for quite a while, but 2,000, 3,000 years is a drop compared to humans, like evolutionary, like time scale for time that we were effectively like modern Homo sapiens, right? And so that's like one possible, I would call it a very convenient and it seems logical like accounting or an answer for like why is physical control problems hard in philosophical sense. And then I also just wanted to go back on I want to say two more things. One, that really humorous showings of like where AI research is right now, especially showing like the old AI video generation, like Will Smith eating spaghetti, like horrifying stuff that was viral. All of this stuff is actually very important for us to do to like keep the public aware of where we're at and where we're not at, but also to show that like humor and novelty is possible. And this stuff constantly captivates people. And so I just want to say that it's good, and you should see something looking a little horrifying, or in this case just funny, as evidence that it's going to look very real very soon. And then finally, on the Plato Cave thing, just throw back to another kind of historical argument that I think this is kind of a similar thing to the Chinese room from Sorel. So I think that's how you pronounce his name, which is, I'm kind of compelled by, honestly, like fictional works such as Ghost in the Shell, and even I would say philosophical systems. I interpret some of the stuff Daniel Dennett says to be sympathetic to this idea that it is plausible even that human minds could be nearly or possibly fully simulated computationally, and that we could create beings that will be increasingly difficult to rule out as having conscious. Basically, even if there's no actual like ghost or spirit or whatever we want to claim is the thing that separates humans from P-zombies, they'll be so dang good at simulating humans. It's going to be like Blade Runner and Replicants. Like, I see that as being the path we are on right now. So I guess my argument is I don't care if they can't like experience conscious reality and that like there's a blurry representation of text and video and all this. I think that basically the bot in the Chinese ruins effectively, like the very fact that humans in extremely contrived circumstances can like autodidactically teach themselves things even with very little practical experience, and in some cases do them highly effectively from like book reading, implies to me that it's much harder. Like, I agree, like we need the physical experience, but I think that it's actually really, this is a road bump and not like a fundamental like impossibility kind of thing, right? Like anyway.
Yeah, I agree. I think like at the end we need both, right? Like we need understanding of the world, like of the physical world, in order to make some things that like looks as trivial, but they are not, right? As robots, right? So we need some understanding of the physical world that maybe we can't get from text, but text, even if it's a blurry representation of humans and human thoughts, I think that it will be so important, and like so important in order to to align models and humans, to align, to understand like how can we interact, how can we communicate. um
And
yeah, very interesting.
well, and I also, AI is too human for me in a lot of ways, with the whole only data and modalities that humans can, or at least most of the AI systems that humans can process, right? So, for example, image, video, text, not a whole lot of smell, which is funny, right? Smell of vision's cool. But there's a whole lot of data modalities that we need complicated instruments to process, and that they can process as effectively first-class citizens. So, like, ultraviolet, right? Like different, types of things that optically we can't see, or like DNA processing or LiDAR or all that. So I see even totally not just superhuman, but very alien looking abilities to kind of create an accounting of physical reality. And this is where, philosophically, for those who might know about it, I am so heavily influenced by Paul, and I'm bad with pronouncing, Paul Feyerabend, who's Karl Popper's student. He wrote, among other things, Against Method, where he argues epistemological anarchism. But his final book called I think it's called The Abundance of Reality or something like that, where he just says, no matter how big you think reality is, it's bigger than that. Like, and we, like, everything you can possibly imagine is just so freaking abundant about this universe that I see infinite potential nearly to create things that both are increasingly so similar to us we can't tell them apart, and so alien that we couldn't have imagined it until we created it because of emergence, that kind of thing. So I don't know, really optimistic, but it's also a little terrifying to think about.
Yeah, I agree. It's a combination, right? Every time, every new model. Yeah. The last thing in our news, AI2 got a lot of money to build open source models, right? To develop frameworks for open source models. I think they got it both from the NSF and NVIDIA. And I think it's very interesting, because, like, right, there are a lot of different kinds of open source, and like this, there is this debate between what it's better like for a company, right? It's like Meta, open source Llama versus OpenAI, right? Or Anthropic, and I think the problem here that there are a lot of different kinds of open source, right? You can just publish the weights, right? And you can download and people can play with the weights. And you can also open source your framework or your pipeline if you want, how you train these models. And maybe the last part, or maybe the most significant one, is the data. And this is something that no one actually
How do you
doing
say
it.
only exception, and why we love
Yeah, that's true. And it's crazy because like data, it's maybe the most important part, and it's the fundamental part that actually change the whole model and affect everything, starting from your training, how you train it, your model, and of course its behavior. So I think it can be very important and very successful if they can actually use this money in order to understand how to make data and how to train on huge amount of data and what you actually need, because there are so many aspects here and so many details that we don't understand. We as a community, right? We don't understand how to train because we don't have the data and all the Chinese models. It's the same thing. We don't have the data. It's very, very important to understand it. And we will talk a bit about different models behavior, and for example that Queen is so weird and has such a strange behavior, right? And my guess is that most of these differences are based on the data.
Absolutely. And I'm fortunate that we've actually collaborated together on multiple data set papers now. And even the very fact that I'm, on a data set and benchmark paper, like first author at NeurIPS, I think most people, certainly the people who are in that track, and even several other heavy hitters have kind of always mentioned, data being the ultimate like backstop, like the most important foundation for which the rest of the field is built on. And in many ways, the bitter lesson is he maybe emphasized it in compute to a certain extent, but it's really in data size, where it's more fundamental. I also think that simultaneous to data sets becoming harder to access publicly post 2022, we're seeing more of the data sets that do exist, more attempts to exploit them further, improve upon them, or annotate them, and even become litigious, as many people in the field are finding, even who have produced potentially benign kind of contributions. And so, I think that's paralleled a little bit by dynamics that we've seen in non kind of AI things, in particular the differences in how you open source things and the importance to the field is very much paralleled by the historical, and they still exist, by the way, in like regular software. There's free as in free beer, and then free as in free, like liberty or whatever they call it, right, to make a differentiation between free distribution of an executable and then source aware, and then of course now for us we have to call it data, which is the very rare one. So I think that there needs to be more of a merging of the historical, like GNU movement and people that care very strongly about software licensing. But also, I just want to point out, as somebody like who is not like I identify with the term copyright abolitionist personally in my like what I want the real world to look like. The fact that Gen AI has been effectively created as an original sin of completely saying, what if IP didn't exist, and then trying to like slowly learn what IP laws are after the fact. I honestly just think like don't learn about it, just ignore that stuff and be like, I mean, not to say like don't contribute all this, but like if we can like rewrite it from scratch and throw the old stuff into the dustbin of history, it would in a metaphorical sense be nice. But of course, really what we need is like the GNU movement, the so-called software communists, who are in my mind fighting a lot of times the good fight to make a big part of their current platform about data availability alongside script model training code and the models themselves. But and I also just want to point out 150 million is probably not that much money, especially the NSF grants, as somebody that's received one, they have not that much scrutiny, at least at the kind of amounts that we've received at. And further, there's already allegations of similar, the Turing Institute right now in the UK is under fire for supposed misallocation of money. Conservative lawmakers there claiming that it's like overran by consultants. I actually won't weigh in on this because I don't have like too much personal knowledge, but there's at least risk, and I would say slightly elevated risk when you're taking money from the government, like grants, of the money not being allocated quite as efficiently as it might be. And when you consider I think that they could be successful at open sourcing really good example of data and even scripts, but I don't think that they're on 150 million training anything that beats GPT OSS, for example, or DeepSeek V3. I'm aware of the 5.5 million, but DeepSeek V3 had $1 billion plus of stuff that went in before that final training run, and I don't see that from AI2. Also, that was a bunch of quant firm folks who did all that, who were hyper smart and hyper capitalist. So, no.
Yeah, so, I'm more optimistic than you, but we will see.
I hope you're right.
Yeah, we will see. Maybe we'll bring someone from AI to talk about it. Yeah. Okay, great. And now to the main part. Let's talk today about parameter efficient fine-tuning of LLMs, right? So imagine that you have a huge model, like at least 7B, but probably much larger, right? And you want to have one single GPU that you want to use, and you want to train your model on a specific problem. Okay, it can be you want to train it to distinguish to replicate your teacher or whatever. And now, how you're going to do it? How you're going to train a model, such a huge model? And the answer is parameter efficient fine-tuning. You have one base model, and you change it a bit in order to fit a specific task. Now, the core, let's say, insight or the core intuition behind all the methods that we are going to talk about is that so it's coming from a very good paper, I think 2021 paper, that called Increasing Dimensionality Explains the Effectiveness of Language Model Fine-Tuning. It's a meta paper that basically said very simple thing. You want, if you want to fine-tuning your model, what you actually do is to change only a small subset of your parameters. Okay, you change some very low dimensional subspace of your parameters, and this is enough to fine-tune on a specific model. So all these huge general purpose models, you don't need to change them a lot. You need to change small amount of parameters, low rank solution, in order to make them very, very good on specific tasks. You want to start explaining us some of these methods?
Yeah. So the first one is this whole class of methods that saying parameter efficient means we don't fine-tune the majority of parameters. But how you can choose to do that, we've made 3 core clusters of techniques, right, that we want to maybe go over and we'll point out that there are probably things that maybe don't even slot in easily into these 3 buckets, but that they are in general either obscure or we've missed them. But I would also point out, just before we go into the techniques, that Hugging Face has a library also called PEFT, which makes it really easy for you to use pretty much any technique that we're talking about here and fine-tune any model that you can locally download and run on your own machine, assuming you have the requisite H100s, of course, right? But maybe I can go into the first big cluster, which is I would call adapters. They've had various names. If you're in the stable diffusion world, you might have heard a term like hypernetworks. But in the more technical academic world, some of the techniques under these were things like adapter fusion, MADX. I think those are some newer techniques. I think that there are some older ones that probably just historically have been referred to as like putting on like an adapter head, I think is the term that it's used for baselines. And the idea with this is that you can add a single, and here, goes to our name, like a bottleneck, like you can take something maybe right before the output or even after the output, adding like a single layer, and the deep neural nets are because we have many layers here. So we take a single one of those layers, we freeze the previous model, and we allow only the adaptation of this one layer at the end. And what's been interesting has been that at least stable diffusion world has kind of concluded for a few years that this is a more primitive kind of technique. Oftentimes the percentage of the parameters that you're going to be training is quite high in comparison to the other techniques, and so there's more of a risk correspondingly, maybe not of actual catastrophic forgetting in the sense of like deleting the weights, but of a sense of scrambling their usefulness by creating new weights that effectively diminish them, so causing a catastrophic harm to quality, I guess. So that's one risk. Then we get another technique. This is maybe cluster 2, which we'll call prompt or prefix tuning. And then this is kind of your if you imagine that each word that you in a language model, for example, it is embedded, like it can create an embedding from this, and it will have a dimension that's quite large. But as you increase the size of your inputs, that you're creating basically a new vector or embedding for each token, and really it's more complicated, but like you can abstractly imagine it like this. And so a soft prompt says, what if you take a very compressed embedding basically from one of these tokens, right? And we can specify the size, so we can say like 16 tokens worth of size here, and it's gonna be tiny, like kilobytes on disk. These are so small you could distribute 10,000 of them or something like in seconds to people. The idea being that this will be effectively tuning oftentimes very, very small percentages of your model's effective like parameter count, and having really a huge impact on style with hopefully not forcing into your model like language. So for example, you can imagine if you put Harry Potter into a soft prompt, it probably shouldn't be using like character names that heavily, but it should be hopefully matching style. Or maybe character names are used a lot, but it wouldn't be matching the specific exact words that J.K. Rowling was using most of the other times, but would probably be very magical, right? And then finally, Laura, maybe I'll let you explain Laura. Ravid.
Yeah, so Laura, like probably like the most famous family of methods, right? And Laura, when we talk about Laura, we talk about let's say family of methods. Laura, it's maybe the most famous one, right? So low rank adaptation of language models. This is a paper, 2021 paper, and the idea is very simple. We want to change the parameters. We want to change some, as we said, low dimensional subspace of the parameters. Okay, so let's use low rank solutions or low rank matrices in order to update it. We don't need more parameters. And how we are going to do it? We're going to do it by decompose decompose the huge matrix, right? Let's say delta W to two different matrices that both of them are low rank. Okay, we constrain their rank and we constrain their size, and we are changing them, and after it we can multiply them and we can get the update for the full model. Okay, so we have these A and B metrics, and we are initialize the A with Gaussians and the B's with zeros, and we are starting to find the right small adaptation in order to get a good solution, and that's it. You can use you need to choose some parameter. You need to choose some what is the rank, or basically how much what is the size of these matrices, and how you're going to change them, how you're going to initialize them, and all these things. But it's very simple. It's very cheap. Like you can get, I don't know, 10% or 5% of the parameters, and at least at the beginning, we thought that it's really good. Like you can it's kind of like, I don't know, no free lunch. We change just tiny amount of the parameters, and boom, we can make such a huge boost in the performance. And we have different variants. We will not talk about them today because we don't have time, but we have QLoRa in order to quantize the model. Okay, so if you want even like to be more efficient, you can quantize the sum of the weights, and you can choose which one to quantize. For example, to use like the 4-bit as the base model, and you can use something, for example, the DORA, that actually split the update to update of the direction and update of the magnitude, and most of the time you learn only the direction, because the intuition is that you want to keep the magnitude the same, right? And what you really care is the direction of your subspace. This is something that you want to learn. So yeah, at least at the beginning, it was look as the best case scenario.
Yeah, and I also want to point out, for all these methods, and maybe LoRa most, they all have, I mean, the rank in LoRa's case is probably by far, well, among the most important of parameters. But you also get, like, by default, LoRa targets, and this is where you can imagine its difference, it's targeting all the layers by of a model instead of only like a frozen layer at the end. And that's why it tends to perform better, is that it can affect the entire model's representations as necessary. But it's also an interesting technique because there's dynamics around the usage patterns of these, which influence community knowledge and downstream usage and code patterns. So what I mean by this is adapters as a class of techniques are still pretty rare with language models, even though they were invented there. There's probably 5,000-10,000 of them, most of them created by researchers. And a lot of that's because it's harder to evaluate them, even with eyeballs, to understand if your adapter made like a meaningful impact on the model versus just getting something out of the prompt. But with Stable Diffusion, on the other hand, there was some serious use cases that motivated people to produce these. And so what I'll point out is that there are hundreds and hundreds of thousands of these, mostly for including characters into the models, into image generator models that were not already included, or styles. And you may need some eye bleach for some of them. But the point in general being that that there's institutional knowledge about the correct way to train these, like the correct settings for these, that is maybe more understood, even if in a hobbyist amateur sense, by folks trying to put in their favorite character into models. And so, academically, I think LLMs and academics are ahead, but in terms of familiarity with these models, I think this is another case, just like LLM sampling, where hobbyists are ahead. And even I want to point out that the equivalent to LLM sampling, like how these diffusion models work, the stochastic differential equation solving is also, I think, something where hobbyists are like ahead here.
Yeah.
But I think LoRa has also been seen. There's methods that are trying to go beyond it right now for this use case, right? SAEs and a few others right now, right? So
Yeah, and I also think that there are a lot of, let's say, open questions here, right? Like now you have a lot of different LoRa's, and now you want to merge them, right? So how you are going to do it? It looks that naively just merge them just failed. Um, so yeah, how you are going to do it? How you are going to use it efficiently, right? Like you want to, for example, you want to change them. You want to change them in really quick way. So what we can, how we are going to do it? I think that it's very open ended area these days. But the nice thing, at least in my perspective, is that almost everyone can try and can test it and can adjust it to their use case and to play with that and to come up with their own version, right? Like you don't need now, I don't know, to 20K GPUs in order to train this model. Again, you can have one GPU and you're fine. Yeah. Why? Maybe let's talk a bit about the cases that it failed.
Yeah, I mean, this is where that term I used earlier, catastrophic forgetting, comes in, right? So the whole point of so catastrophic forgetting is the idea that in traditional full fine-tuning, which this PEFT is opposed to, you're overriding these painfully, it took billions of dollars of effort to create the magic numbers that are the weights in your model, and you're going to overwrite that with your much lower quality information, much lower amounts of it, probably worse methods. And so but actually for some people, you want to use full fine-tuning. So for example, what we would call continuous pre-training, which is a type of fine-tuning and is probably the most pure form of it, where you just say, hey, I have new data I want you to do your next token prediction task on. And that's actually really good for adding new information, and is indeed almost certainly how you're able to go from GPT-4 to 4.1, where you're adding new information to the model's like pre-training like data set, right? And that's very desirable for a lot of customers, I actually claim. And then you get limited expressivity. So there's possible parts of your model that you want modify, and it's hard to say. I mean, the whole point of what LoRa is doing is that the low rank representation that it modifies is supposed to have very high impact, right? Uniquely high. In a mathematical sense, it's analogous kind of to PCA, if you're familiar with like eigenvalue decomposition. So I think that it's if you're trying to make a truly large impact on a model, the limited expressivity really hurts you and can possibly act as a ceiling on the possible performance you can unlock. And I'll just finalize by saying that, as with all types of fine-tuning, that a lot of people who think they need fine-tuning are perfectly happy with RAG. And the ability to perfectly delete information instead of go into the extremely haphazard and very much like machine unlearning. Yeah, we have papers on it, but no, it doesn't work yet. So no, anything you put into the model, it's no guarantee you're getting it out. So
Yeah, I think I agree with you. Like at the end, it's kind of like the same thing with RL, right? Like you think like you can use it only if your model already has it in their weight, or like in their inside the model, right? Like you just want to reveal this information, or like to understand like to learn to teach the model how to use it in like to just format in the right way, or like structured in the right way, or just tune and align your model a bit. If you want something fundamentally different, so no, it will not work. But if you just want to learn, you want to do bit personalization or to adjust it, go for it. I think this is it's a great example of this trade-off, right? That like constrain your model is very easy to train, very easy to deploy. You can do it really fast, but at the end, it doesn't change the fundamental behavior of your model. And we can see it many times. We can see it many times. As you said, when you think you delete something from the model, you probably didn't.
Yeah.
Yeah. Okay, cool. So yeah, I think like, do you have anything else that you want to talk about with Laura?
Oh, yeah, just a quick note on merging. First of all, you can model merge anything, including full models with each other. And I had a friend of mine who coined the term a new chemistry of ideas to refer to what generative AI can, in theory, give you. Which I believe, like, the analogy of, like, pouring together substances and stuff is really, really great, because it shows just how continuous everything is. Like, I like, do not believe that, like, reality is quantized because of AI. Like at the fundamental, like, I think there is something under, like, Planck length kind of stuff. Like, so that nature is fascinating, because I actually have been reading a paper titled "On the Union Groundedness of Generation," something like that. Basically, this is a theory, very heavy theory paper, and I'm not very good at theory, and maybe I'll put in the proper name of this in the transcript for those who care. But the paper goes in and basically throws bathwater on this idea that model merging is like theoretically justified. So like, and when we say model merging, we're referring to, like, in some cases, mathematically averaging the weights of two different models, or in the case of Laura, the delta matrices with the base model. And there's far more, like, weird math you can start doing. You can basically just invent your own math operations with these matrices and be like, wow, in this one data set, it's way better. Nurick's paper for a new model merging method. And this theory paper really tries to claim that model merging will always have, like, damage, and that it should be avoided unless you're doing, like, inference time creative stuff, which is mostly how it's used. Not just, like, LoRa's are mostly being used by that, like, stable diffusion community, but model merges are similarly hundreds of thousands of them, because of people wanting to merge, like, some anime style with, like, ultra hardcore realistic and get, like, a new thing. And I like this, by the way. I think that in terms of trying to analyze, like when I even think that you can start mechanistically seeing reality or computationally, like, being able to look at a particular artist, it's obvious to us humans when somebody is influenced by something. And maybe nobody wants to admit that, like, Elvis is 20% bluegrass jazz with 15%, but, like, that's effectively possible, at least to simulate with all these techniques, and nearly every part of things that involve floating point numbers and machine learning has these properties of creatively being able to mess with them and see what happens.
Yeah, I agree. I think it's also related to, like, the concept of uncertainty in models, right? I think maybe, let's say, 4 or 5 years ago, there was a huge debate in the Bayesian community that it's not so big community, so that's fine if you don't know them, but so apparently, at least in the past, right, for vision models, ensemble methods were much better. What is ensemble? You just train different models and you average them. You average the prediction or the weight or whatever. And apparently it worked much better than a classical Bayesian methods that try to make Bayesian learning and Bayesian inference and things like that. And there was a huge debate why it works better, and, like, how actually we can bridge this theoretical gap, right? Because Bayesian learning should be better than just simple ensemble. And again, people did a lot of theoretical tricks in order to solve it. I think that it's a bit broader discussion, but I think like theoretical insights are limited in this area, if you ask me, at least in this time.
There's a lot of good theory that says that things that we know are state-of-the-art empirically are dead wrong, right? And don't
exactly
listen to the theory, nothing would get done. But
exactly.
I'll just quickly, like Bayesian, Bayesian priors, terms like that, attempts to kind of invoke him are used even in like rationalist communities, like people in Silicon Valley. And I'm fascinated, when you talk about like averaging, I mean, the convolution operation, right? What is that doing? It goes through many pixels in a grid and it averages them. So it's violating this like Bayesian kind of assumption too. And I think that like the fact that works and arguably probably still does. I mean, my understanding is that jury's out on if CNNs are obsolete compared to transformers or not in image recognition. I have to go see, but at least a few years ago, there was some evidence that CNNs are still really great. So, I think Bayes, like I love the elegance of it and the theoretical, usage of all information, but I think that it's sad as to how little practical influence Bayesian statistics have in general. And despite its element, I feel like it's the functional programming of statistics.
I love Bayes' theorem and I love Bayesian people, so
yeah.
But I agree. Okay. Do we have anything to say more about LoRa or anything that's related to efficient fine-tuning?
Well, so you already mentioned that it's computationally easy, but specifically, you're like, if you have a MacBook Pro, like an M2 series, for example, or greater, you should be able to take like at least a 3 billion parameter and probably a 7 billion parameter model and be able to do a meaningful like adapter training on even, one way you can test this is on like writing transcript logs. And I can tell you that I've actually created some adapters of like my own writing style, which is painfully obvious by my overusage of quotes, parentheses, general wordiness, everything. I look very different from ChatGPT when I'm writing. And I get output that starts looking more like and it also seems to have like harmed models a lot of times in their like reasoning capabilities, and maybe that's because I'm a little bit dumb, but more I like to think that that's because of the harm, the little bits of catastrophic harm to the model representations. And I also wanted to quickly point out the connection here. Like if you solve the problem of harming model representations when you keep training, you've effectively solved the problem of online learning or incremental learning, which means that now our models can learn on the fly, which is the way that a lot of people like in the public colloquially think that models are like continuously pre-training and adapting on the fly when they're being used at inference time, which is most of the time not the case. When it has been the case, it created things like Microsoft Tay, where 4chan users caused it to be racist within like seconds. And so it's considered like dangerous both to expose to the public, but also just like dangerous for your model like quality. And PEFT has been seen as a candidate style like paradigm to kind of like go and make incremental learning work. So that's one note, just very promising kind of direction and connection to things. The other note I would say is the software for doing training like this. We talked about PEFT from Hugging Face. I know that there's some GUI tools, right? The Uba Booga text generation web UI has LoRa training built into it, as well as Comfy UI has the tool that Comfy UI is built on, called Automatic 1111, also has LoRa's built into it. So LoRa training, and I think regular adapters. So that can make it a little bit easier, but you're still going to need to like watch some videos and follow some guides. And honestly, like figuring out the correct settings is, whatever you're seeing in the videos is hobbyist approved numbers. It's like, nobody really knows what they're doing in this field, even the academics. So be ready for a lot of trial and error with this.
No, I totally agree. I agree, because like you remember that like at some point we did a lot of like LoRa fine tuning, doing personalizations with a lot of personas, and a year ago it was much harder, right? Like it was like, what are the right patterns? How are we going to do it? And it was a lot of math. I hope it became better in the last months. I think it is. I think it now it's much easier to do.
Yeah.
Okay, cool. Let's talk about briefly about a very let's say surprising paper. That is not related to LoRa or something like that. It was just very weird and surprising paper. And we were talking about spurious rewards, rethinking training signals in RL VR. It's a paper from Luke's group in Washington, University of Washington, and they basically showed very weird phenomena. They trained their model on reinforcement learning with verifiable rewards, and they trained with different kind of reward, right? So if you don't know, in reinforcement learning with verifiable rewards, you have your model and you come up with some examples and some samples, and you send these samples to some verifier, and you get the reward how good these samples are, and then you train the model based on these rewards. Now they showed that in some cases, and specifically for Quen models, you can use random verifiers in order to get good results, and in order to get much better results than the base models. And it's not only like, to very specific data set, and it's you can generalize to other data sets just using random rewards. Think about it, it's crazy. Now, in the paper, they also show that they suggested that it's related to the code generation ability, and they show that you actually the model learns to generate more code, for example Python code, and they suggested that it may be that like now it has more compute, right, to run and like to validate its answers basically. But I think it's very hard to understand. I think we are really far from understanding what is actually happening in RL, and why it helps, and in what cases, and why Quen is the only model that actually it helps, or a lot of different questions that we don't know yet.
Yeah. The Quen has been, that whole thing of Quen being a really weird, in a good way, model has been a theme in a lot of research. As I recall, it was also the sloppiest model on the anti-slop index, and but simultaneously to it being slopped, you can deslop it the easiest in the fine-tunability of it, and so that part's nice. I also wanted to point out, we didn't plan to talk about it too much, I guess, but you did send to me a link about this. It's titled "Incorrect Baseline Evaluations Call into Question Recent LLM RL research," basically, and they actually point out this spurious reward paper might have some issues. Now, I don't want to take too strong of an opinion, and even if the paper has issues in methodology, it's quite, I would say, easily possible that they're still right, that like random rewards work. I also want to point out that I think that people have used or worked with verifiable rewards for a long time before the term was coined. For example, I know that there have been experiments with just showing, hey, stable diffusion, you can just say, even at inference time, but also at training time, simultaneous to you following the stable diffusion objective, you also have the objective of generating blue pixels from this coordinate to that coordinate. And so you can force the image to be like more blue in some places. And so I think that the most of the time when we're trying to talk about good verifiable rewards, we're thinking like, okay, generate code, run it through code interpreter, and then code interpreter tells you this runs good or this doesn't run bad, and then using that as feedback. I think that it could be that my hypothesis on why this might have any effect is that things that we thought were random weren't really that random, but also there's an even more spooky possible explanation, which I would admit is very fringe, but somebody at Anthropic would probably believe this because Anthropic has published research along this. Their research is claiming that models basically know in some sense when they're being trained, right? And that there could be something epistemologically about the act of having reinforcement, even if it's bad, that's like grounds the model in some way. I don't know.
Yeah.
That seems pretty.
My guess is that like everything is also like related to information and how you actually manage information and how you control and compress information. But yeah, you probably can look on some of the recent papers, and maybe hopefully we will have a better answer soon. What is happening in RL in general and why it's happening. I think it's still an open question.
Well, there's super determinism, right? All things are correlated with each other, even things you think are not correlated.
Right, that's true. Everything is information. This is the main message of this podcast. Okay. Anything else, Alan?
On this paper?
In general?
Oh gosh. I would, just going back to just a quick other connection. The person that was a little bit critical of the bitter lesson was I think they were also kind of complaining. It was them and maybe actually, sorry, the Sergey blog post, right, saying LLMs like a prisoner in Plato's cave. He also made a point about how like LLMs need to be able to learn on the fly, and I think that a lot of the arguments will be mitigated of this whole physical 3D control being so hard because for example, even when the robots are running around in the Chinese robot games, right? I think that was held in Beijing, right? They're not, I don't believe most of those are learning on the fly from feedback. And that's, like I said, people complain about the guiding star being about creating AGI and ASI. If you just make the guiding star continual learning, I think that will make a lot of people happy. And I've been telling, I always say this, you will get a Turing Award if you solve that. Like, you will be probably seen as one of the most famous humans in history for solving that, if you can do it. I think it's like up there with turbulence and quantum physics on like hard. So
yeah, I agree. We just need to solve it. No problem, right? Easy. Yeah. Okay. Thank you so much, Alan.
Yeah, you too. It's always a pleasure.
See you next week. Bye, everyone.